forgot, so he probably, I don't know, he may be listening anyway, I don't know. Any questions, anything we've done so far? Except why aren't you turned on the projector? I'm not going to answer that question. Okay. Any other questions? All right. If not, we're right at the end of 2.2, example 9. And we're just going to verify something we talked about last time. Here's two matrices. Whoa, let me get my pen set up. Whoops. Can't get my pen set up. There it is. Okay. Here's matrix A. 2, 1, negative 2. Negative 1, 0, 3. 0, negative 2, 1. Here's matrix B. 3, 1. 2, negative 1. 3, 0. Okay. It says to show that AB, what's that superscripted T stand for? Transpose. And B transpose, B transpose A transpose are equal. Okay? So what's the first thing we've got to do this one? First one. Multiply A times B. Can that even be done? Why? Okay. A is a 3 by 3 and B is a 3 by 2. So since the inner numbers are the same, you can do it. What will the answer be? What size?
That's going to be 3 by 2.
3 by 2, absolutely. All right. First entry. The 1, 1 entry would be what? 6 plus 1, 1 entry. First row of A times first column of B. 6. Help me, folks.
6.
Not that hard. 6 plus 2, right? Second? The first row of A times the first column of B. 6 plus 2 is 8. Second? Oh, do I have it right? Okay, good. Okay. All right. Okay. Try it again. This is 6 plus 2 is 8. 6 minus, no, 3 times 2. Minus 6 is 2. Yes. The plus 6 and minus 6 go away. So that's the 2. All right. Which one you want to do next? 1, 2 or 2, 1? Or any one of them? Which that? 1, 2. Okay. That'll be first row of this one, second column of this one.
6.
Second?
The
2.
solution to 6.
Second?
2.
2. Minus 1 is 1. Okay. And then?
6.
That's a 0. So that's just going to be a 1.
I'm on the wrong side. I went the wrong world.
Okay.
You're right. I'm wrong.
All right. Where do you want to go now? Choose. And this looks like a 4, but that's a 0, I'm pretty sure. Okay.
Second row.
Second row,
First column.
first column. Okay, what does that give you?
They're actually going to be 6.
Okay. It starts with a -3, a 0, and a +9, so yeah, the answer is 6. You're absolutely right.
That's where I was at.
Oh, okay.
That's all, you know.
All right, where do you want to go now?
Right on,
Second?
third row. First column, third row.
Okay. Third row, first column. Okay? So that would be a
-1.
okay. A -4 plus 3 is -1. Perfect. Okay, next. Next.
-1.
All right. Second row, second column. Okay, -1, and 0, and 0. That's -1. Perfect. Next. Two. Perfect. Okay, now that's AB. What's AB transpose? What size will it be? 2 by 3. And what will be the entries of that? 2, 6, -1, 1, -1, 2. Good. Now we got to do B transpose. B transpose is what? What size will it be? 2 by 3. So its entries will be 3,
1.
okay, where are you now? B transpose. Just tell me where you're.
Oh, I went to the,
Second. You were going down?
yes, sir.
Okay, yeah. So 3, 1, that would be correct.
Two,
-2, -1, and
3, 0.
0. Okay, that's B transpose. Now we need to do A transpose. What size will it be?
3 by 2.
3 by 3, of course. And what?
3 by 3.
Okay, and what will be its, give me either first row or first column, I don't care. Just tell me which one you're doing.
First row.
First row is what?
2,
2,
6.
what?
Oh, 1. Sorry.
Okay, no. If you're transposing A, are you doing column or row? Row, okay, give me the next entry in the first row. -1, 0. Next, 1, 0. Second, -2, okay. And what? -2, 3, 1. Okay. Can you multiply those two together? Why? A 2 by 3 times a 3 by 3. What size will the answer be? I'm sorry? Yeah. Did I hear a 2 by 3? Okay. All right. First entry will be, okay, I see a 6 to begin with. Then there will be a -6. So it looks like a 2, doesn't it? Is that what you said? Okay, I can't hear well. Now, are we going across or down? I don't care. Across, okay? The 1, 2 entry would be 6. And 1, 3 entry would be -1. Okay. 2, 1 entry would be 1. Is that what you said? Okay. I've gotten lost here. Okay. 2, 2 entry. Yep, -1. And 2, 3 entry. Second? 2. All right. Looky here. These two are indeed equal. Okay? So sure enough, AB transpose is the same as B transpose times A transpose. Good deal. Any questions on that? Okay. Now, let's get to another situation that you might find interesting or not. Let's do a matrix A. A 1, 3, 0, -2, -2, -1. Find the product of it and its transpose. What would be the transpose of A? What size will it be? 2 by 3. And what would be the entries? 1, 0, -2, 3, -2, -1. Can you multiply those two? Said yes. What will be the size of the product? It will be a what? 3 by 3. Absolutely. 3 by 2 by 2 by 3 is a 3 by 3. So 1, 2, 3, 1, 2, 3, and 1, 2, 3. First entry. Ten. Okay, you going across or down? Across. Okay, next entry will be a -6. Next entry will be a -5. Okay. 2, 1 entry. -6. 2, 2 entry. 4. 2, 3 entry. 2. All right. 3, 1 entry. Second, -5. 2. Second. 5. Okay, good deal. Now, I don't know if that strikes you with any. Does anything seem special about that? Are exactly the same. We call that a symmetric matrix. This -6 and that are the same. 5 minus 5 minus 5 are the same. 2 and 2 are the same. Doesn't matter what the diagonal is. That doesn't have anything opposite. But everything on opposite sides of the diagonal, main diagonal, are paired with each other, and that's absolutely that way. Now, it says show that it is symmetric. That's definition of a symmetric matrix. Now, we did A prime, okay? A transpose, okay? And they got the same thing we did. Good for them. So what would be now that's one manifestation of it, but actually the classbook definition of it is that to be symmetric, the rows and columns have to be the same. 10, negative 6, negative 5, 10, negative 6, negative 5. Negative 6, 4, 2, negative 6, 4, 2. Negative 5, 2, 5, negative 5, 2, 5. Okay, so the rows and columns are the same. Same thing you said, but it's that's the way they define a symmetric matrix, that A transpose is equal to A transpose, okay? That the whatever the matrix is equal to its transpose. That's what makes it symmetric. Okay. Now, what they didn't do, and I thought they probably should have, is have you do A transpose times A. Can you do that? I'm going to erase this part, though that is the formal definition of a symmetric matrix. Let me write the A over here. 1, 3, 0, negative 2, negative 2, 1. Can you do A times A transpose times A? Can you? Yes, you can. What size will the result be? 2 by 2. What's the first entry? Second? 5. The 1, 2 entry? Help me, somebody. Second? Okay, that'll be 3 minus 2, right? Second? Is it negative 1 or?
No, I had wrote down a negative 1.
Oh, I see. Okay. Wait, you may be right. It is a negative 1. I'm the one that blew it. Okay. Sorry about that. Okay. So let's do that entry again. 3 plus 2 is 5. Goodness gracious. Okay. Next entry. 3 plus 2 is 5. And the last entry is it 14? 9 plus 4 is 13, plus 1 is 15. No, okay. Is it 15? Wait, I hit the wrong key. Okay. Okay, let me see. 9 plus 4 is 13, plus 1 is 14. Okay. I believe that's right, right? Okay, now this is a lot harder to tell, but sure enough it's symmetric too. It only has one opposite thing, and they are the same, but the rows and the columns are equal to each other. So that's also a symmetric matrix. 2 by 2, all it takes is two numbers to be the same and it's symmetric. Okay. They didn't have us do that. I did it. And it is symmetric. Well, that wraps up. Oh, there is a linear algebra applied at the bottom of page 58. And it has something to do with, I guess it's talking about search algorithms. I don't know for sure. What company was founded on a superior search algorithm? Second? Google, okay? They came up with one, as far as I know, it hasn't been beat yet. And of course, it's very proprietary. No one knows exactly what their algorithm is. I bet you a lot of people have some pretty good guesses. And I bet you a lot of people have copied it as much as they could figure out how to copy it. But Google built their fortune on that algorithm. The two co-founders, one of them did most of the development on it, though I think they both worked on it, and the other one was really, I think, the marketer or something. I've heard different things. But anyway, guess what? Linear algebra is all over it. You know, any search algorithm, linear algebra is there. Okay. So, 2.2 exercises. Do any of the odds 1 through 5. They're all at calcchat.com. And they all have answers in the back, too. But at calcchat.com, you get to see worked out solutions to those odd number exercises. Any of the odds 7 through 11, 13, any of the odds 15 to 19, 21, 23, 25, 27, any of the odds 29 to 33, 35, 37, either 39 or 41, 43 or 45. There's a true false 47. They should all be at Calc Chat. There's 49, 51. Now that's sort of an interesting one. Finding the power of a matrix. If you can keep your matrix simple enough, you could do all sorts of powers with it. Okay? That should be at Calc Chat. 53 should be at Calc Chat. 55 should be at Calc Chat. And then we have 57 through 63 are either guided proofs or proofs. Okay? Oh, I'm sorry. Even 65. So you can choose to do those or not. They're up to you. 67 and 69 should be at Calc Chat. And they have a new definition there. I'm trying to think where they gave that. Skew symmetric. We know what symmetric is, but I can't remember if they've given us a definition for skew symmetric. Did they give that back in the previous set of exercises? I don't know. You'll have to check. Seems like they did. I just don't remember which set of exercises it was. So maybe in the back of the book you can find that. All right, so either 7 or 69. Then some more proofs, 71 or 73, if you choose to do those, and 75. All those should be in the back of the book. All right, any questions on 2.2, which was matrix operations, I believe the title was? Properties of matrix operations. So let's move on to 2.3 if there are no questions. 2.3 is dealing with the inverse of a matrix. Okay? Sort of bizarre. In my morning pre-calculus algebra class, we were doing inverses of functions. Now we're doing inverses of matrices. It's sort of like today's an inverse day. All right. Let's talk about how you solve an equation. Now this is way too easy, isn't it? If you had AX is equal to B, how would you solve that equation for X? Second? Divide by A. Divide both sides by A, and that would give you X is equal to B over A. Or, another way to express that would be the reciprocal of A times B, right? Because 1 over A is the reciprocal of A. Okay? Now, They put a 1 out in front. I don't know why, but that's your answer. Reciprocal of A. Now, the number A to the minus 1 is the multiplicative inverse of A, because A inverse A to the minus 1 times A is equal to 1. Multiplicative inverse. 1 over 7 times 7 is 1. Okay? The identity element for multiplication 1. Now, the definition of the multiplicative inverse of a matrix is similar, and let's see what it is. At least the representation is similar, but it's a completely different issue. Let's say we have an n by n matrix, A. And we're going to talk about being invertible. Okay, that A is invertible. Now, another name for that is non-singular. Okay, non-singular. If it's invertible, it's non-singular. When there exists another n by n matrix, okay, B, such that, now here's the requirement, AB is equal to BA. Whoa! Most of the time that's not true, remember? That multiplication is usually not commutative. If you multiply A times B, now if they're both square matrices, you can do this, okay? You can do B times A, but most of the time that's not going to be the same matrix answer. Just isn't going to happen. In this case, it is. If this is invertible, if there is such a matrix, B, such that A times B is equal to B times A, and that product is not just that it's the product is the identity matrix. So whereas before we had 1 over A times A, which is A inverse times A, is equal to 1, here we have A times B, which is the same as B times A, and that happens to be an identity matrix. If that condition is met, then we say that B is the inverse of A and A is the inverse of B. Okay? It's not a reciprocal, it's an inverse. Okay? Where I sub n is an n by n matrix. Well, the wrong one erased. Okay. Identity matrix of order n. Okay. The matrix B is called the multiplicative inverse of the matrix A. Okay. A matrix that does not have an inverse I can't spell, does not have an inverse. Goodness gracious, how does this happen? Okay. Does not have an inverse is called non-invertible or singular. Okay, so if it's invertible, it's non-singular. If it's not invertible, it's singular. Okay. If it has an inverse, it's invertible, which is non-singular. If it does not have an inverse, if you cannot find a matrix B that you can multiply it by A and get the identity matrix of the right size, n by n, then it's a non-invertible or singular matrix. Okay. Now, when we're talking about inverses, you have to be talking only about square matrices. A rectangular matrix that is not square cannot possibly have an inverse. So don't even try it. Okay? It can't. So for this section, inverse of a matrix, everything's square. If it's not square, hang it up. There is no inverse. All right. Now, oh man. Because note, if A or B was not square and of the same size, then A times B, you might be able to do it if this is a 2 by 3 and this is a 3 by 7 or something like that. Yeah, you can multiply them, but then it's sure not going to be that straight. It can't happen. That would be a 3 by 7 by 2 by 3. No, you can't do that. And it certainly wouldn't give you an identity matrix of the same size as those are. So these have to be square matrices. Not only do they have to be square, but it must be so that they, when you multiply them, commute the multiplication, it gives you the identity matrix. It's not just that it's equal, but it's also equal to the identity matrix. Okay. Now, here comes the theorem. If A is an invertible matrix, if A invertible, okay, what that means, it's got to be square, and you can find an inverse. Okay, if it's an invertible matrix, okay, then the inverse is unique. Okay. And the inverse is A inverse. We even use the same -1 superscript like we did for 1 over a number A, meaning a multiplicative inverse. But here it doesn't mean multiplicative inverse. It means inverse matrix, which is in some senses sort of a conceptually somewhat similar, but definitely not evaluated the same. Okay? Now, the proof of this is pretty easy, I think. If A is invertible, which is told us here, then that means there is a B such that A times B is equal to I sub n. Okay. So if A is an invertible matrix, then in order to get a square matrix of the same size as the product, then the B has to be the same size. It also has to be square and the same size. And if this produces an identity matrix, then those two are inverses of each other. All right. Now, let's say, and this says the inverse is unique. Let's say there's another matrix C. Okay? Oh, and by the way, that is also the same as B times A. Okay? Because you can commute if they're inverses of each other, and it will give you the identity matrix. Let's say there is another matrix you can do that with A, that you got A times C is equal to I sub n. Okay? No way they well, let's just say there is that. Well, if that's the case, then that's equal to C times A. Because if there is another inverse for A, call it C, and we're assuming that C is not the same as B. Okay? Now, how do we show that those are equal? Okay? Well, what if we multiplied this by this other matrix C? Okay? Then this would be C times I, right? Now, if you rearrange that and make it, let me get this one out of the way.
Would it be AB?
Second?
AB?
Okay, what about AB?
No, don't worry about
Okay, all right. So one of the properties of multiplying matrices, as long as they're the right size and all these are square and the same size, that means we could do CA times B, right? Just rearrange them. Move the parentheses there. Okay? And this, I wish I hadn't erased it now, is I sub n times B would have to equal, and C times IN would be C. Okay? But IN times B is just B, so B is equal to C. Hey, they're not different matrices, they're the same matrix. Okay? That's a sort of a common technique, you know, use the identity matrix to help you get there. So, because the inverse matrix A inverse is an invertible matrix and is invertible of the invertible the inverse A inverse of an invertible matrix A is unique. You can call it the inverse of A, not just an inverse of A. So in other words, A times A inverse is equal to A inverse times A, and that's, when you multiply those together, you get the identity matrix. Okay, I was about to forget where I was heading on that. All right, let's do example 1. I didn't get to finish lunch, and I'm feeling it right now. Ugh, I'm hungry. A is equal to -1, 2, -1, 1. B is equal to 1, -2, 1, -1. Okay. Two matrices. All right. All right. Now, I think what they're asking us to do here is see if these two matrices are inverses of each other. So let's do A times B and see what we get. Can we do it? Sure, because they're both 2 by 2, so the answer is going to be a 2 by 2. All right. Where do you want to start? First row, first column. So let's do that. -1 plus 2 is 1, right? My pen keeps dragging a little bit. Goodness Yuck. My wife talked me into getting this. It was free, but I really don't like it much at all. I'm not used to it yet. But I was trying to wipe my eye. But let's go on. What's the next entry?
2 minus 2.
Say again?
2 minus 2.
I can't hear her well.
Oh, sorry. I have a limit on. Oh.
Yeah.
2 minus 2.
Right, which is?
0.
0. Got it. Next?
Negative 1 plus 1.
0.
And 2 minus 1.
1. Hey, that's the identity matrix. And it's a 2 by 2 identity matrix, I2. Okay? Now, is that enough to show that these are inverses of each other? Well, frankly, I think probably so, but they just about always then will also do BA, just to make sure it wasn't a fluke. So let's do the A over here, which is minus 1. Yuck. Minus 1, 2, minus 1, 1. Okay. Can you do BA? What size will it be? 2 by 2. And let's do it to it then.
Negative 1
Right?
plus 2.
Right?
1.
1. Next.
Across, 2.
Right? 2 negative 2 is?
0.
0. Next
And negative 1 plus 1.
is 0.
0.
And
minus
1. Sure enough, that's also the identity matrix, the 2 by 2 identity matrix. So certainly these are inverses of each other. Can it be that one of them will turn out to be an identity matrix, but when you commute it, it won't? I've never seen it happen, but they always do both of them just to see. Now we get around to finding the inverse. They've given us the inverse and says show that they are. How do you find it? Okay. Now this is going to take a while, and it's kind of a little bit on the tedious side. Okay. So here we have a matrix A. This time it happens to be 1, 4. Negative 1, negative 3. Sorry. Okay. Now, we want to find its inverse. So if it does have an inverse, that means that when you multiply this by, I would use A's, they use X's. X11, X12, X21, X22. There's the unknown matrix that we hope is going to be the inverse of this. And when you multiply those two together, you're supposed to get what? If that is the inverse of it, what is your product supposed to be? The identity matrix, the 2 by 2 identity matrix, which is 1, 0, 0, 1. All right, let's do the math. Okay? Do this one. X11 plus 4X21 is equal to 1, right? Excuse me. And then let's do the second row, second column, and that would be X12 plus 4 x22 is equal to 0. Next, you tell me. Negative x11. Negative 3x21 equal 0. Okay? And finally, oops, I put the wrong, no, I did it right.
Oh, it's going to be plus 4x.
Okay, wait. You're doing the, okay. It takes a while to get up. My knees have been hurting. Okay. This one we did, x11 plus 4x21 is 1. Okay. This one we did, x12 plus 4x22 is equal to 0. This one we did minus x11 minus 3x21 is equal to 0. And this one is minus x12 minus 3x22. You see? Is equal to 1. No. Because that fourth entry is a 1. Now, I should have spread those out some. I wasn't planning ahead well enough. But that's the start. Okay? And like I said, this is tedious. Okay? Tedious. Okay. Now, if you did what I kind of indicated here, x11 plus 4x21 equal 1, and minus x11 minus 3x21 equals 0. Okay? Okay. Then do the two others. This would be x12 plus 4x22 equals 0, and minus x12 minus 3x22 equal 1. Now, that kind of sets us up the matrix again, doesn't it? Okay? Not that we really want it to, but that's what it is. Now, if you were to solve this first system here, which you can do, right? Just add these two together, and you eliminate the x11, and that gives you x21 is equal to 1, right? And if x21 is equal to 1, then go back and plug in, and you have x11 plus 4 equal 1, so x11 is equal to a negative 3. Okay. All right. So x21 is 1, x11 is negative 3. Let's do the same things here. add the two together, and you get x22 is equal to 1, and then plug that in either place, and you get x12 plus 4 is equal to 0, so x12 is equal to negative 4. Okay. So your X matrix, X, put the ones in their place. X11 is negative 3, X12 is minus 4, X21 is 1, and X22 is 1. Okay. Negative 3, negative 4, 1, 1. Now, it says multiply that by that, A by X, and see if you get the identity matrix. You sure should. Okay. All right. All right, now, this is where they make it sound so simple, but I don't, in my mind, it's not as simple as it looks, or if they make it seem. Let me see, how are we doing on time? Is it time?
1 minute.
Huh?
Yeah, 1 minute.
1 minute. Yeah. Okay. Yeah. Now, I probably didn't solve it the way they wanted me to. It was just so easy to solve this way. But basically what you had was this. You had 1, 4, 1, minus 1, minus 3, 0. And you solved that and you came out with this. Over here you had 1, 4, 0, and minus 1, minus 3, 1. You know, if you did Gaussian elimination, right? Well, here's the key. What if you had just combined those two, because this part was the same on both of them. What if you had just taken that and multiplied by the identity matrix, adjoin it together? Here you adjoin just the solution matrices, but what if you did it all at one time? Okay? Here's what you would have gotten. Okay? You'd have gotten the 1, 4, negative 1, negative 3, 1, 0, 0, 1. Now do your Gaussian elimination as you're going. And as you do, this becomes the identity matrix. And what this becomes is your inverse. That's the technique we're going to be using. Okay? So you row reduce this, and you wind up with the identity matrix transforming to become the inverse matrix. That's where we'll lead off to next time. And I think we'll do that starting with that problem right there. We'll start right there. I'll move this arrow up 1, and we will move on from there. Let's see if we got enough done to do any homework exercises here. Yes, you can do any of the odds 1 through 5. And then hold off finding the inverses. We'll do that next time. with 7. So you can do 1 through 5. All right. And now we're out of time, right? That sort of flew by, didn't it? Well, we got started late too because of my being stopped in the hall. Sorry about that. But we should finish 2.3 next time and move on to 2.4. 2.4 is going to take a little longer to do, but not super long. And then I think that's it for chapter. Nope, there is a 2.5, but we're not going to do very much in that. I'll just sort of generally talk about it, but we're not going to take the time because that is a rather tedious set of exercises. So we'll go on from there. All right, good deal. We will